Okay, so we're going to go over part 2 of topic 4, and we're going to start with example 4. So just as a recap, we had done example 3 in the last video. We used Cartesian vector coordinate systems to determine the moment produced by the force F about point O. And now we're going to move on to another 3D system here that has two forces acting on a rod. And what we want to do is we want to determine the resultant moment, very similar to example 3, that both of these forces create about the flange at point O. And again, we wanted to express these results, or this result, as a Cartesian vector. So the first thing I'm going to do, I'm actually going to redraw this, and I'm going to redraw it so we can figure out what the position vectors are to get to A and to point B here. So you can actually draw this directly on the diagram, or you can create your own the way I'm going to do here. It's kind of like a free body, except I'm actually going to add on the position vectors here. Okay, so point A is located directly on the y-axis. And that means to get to point A, I would have some position vector that I'm going to call RA from my origin at point 0, or O. And then I have point B somewhere around here, right? I'm given the x, y, and z coordinates of that point, which I'm going to use to generate that RB vector. And my RB vector is going to be this position vector here to get from point O to point B. And then what happens here is I have two forces. I have one force acting at A. I'm going to call, or the problem is calling this force F1. And then I have a force acting at B, which is called F2. I want to make sure I draw that so it's not in any one direction, kind of. It's a little hard to see. F2. Okay, and both of these forces have components in the I, J, and K directions, so they're not acting in any specific 2D coordinate system or 2D plane here, okay? So now if I want to specify the RA vector, as you can see, it's purely on the Y direction, so I'm just going to have to travel 5 in the J direction to get to point A, and that's pretty much it. And for B, position at B, I'm going to have to travel 4 in the X direction, a positive 5 in the J direction, and then a negative 2 in the K direction in order to get to point B. And I got that all from this diagram up here. Okay, and now, since we have our position vectors, we know that our resultant moment about point O is just equal to the sum of all of our position vectors cross product with the forces. So basically this is equal to position vector at A cross F1, the force there acting at point A, plus the position vector at B cross F2, which is the force acting at point B. So now all I have to do is plug these two cross products in. So I'm going to have I, J, K direction. I have the position vector for RA, which is 0 in the I, 5 in the J, 0 in the K. And then I'm going to directly take this F1 and plug it in right here. And I'm going to plug in that negative 60, 40, and 20. And then I'm just going to add that to my second cross product. So again, I have the I direction, the J direction, and the K direction. And now I have RB, which is just 4, 5, negative 2. And then I have an 80, a 40, and negative 30 for this F2 here that was given in the problem. Okay. Now I can use my cross product function that I wrote earlier on a previous slide to solve out for each one of these. I'm going to put that here. So the first step, I'm going to take that 5 right here. If you guys might remember this, taking the determinant. You can either do it directly. So I would be this, these two multiplied by this 2 subtracted. This might look familiar. J would be this multiplied by this minus this multiplied by this, and then K would be these 2 multiplied by, subtracted those 2. That's how you get the determinant. Okay, so I'm basically just going to go through that process, or again, you can use the equation, whichever method you prefer. I direction minus 0 in the j direction, plus 0 times 40 minus 5 times negative 60 in the k. That's for the first one right there. The second one, I'm going to have a plus 5 times negative 30 minus 2 times 40 in the I, minus 4 times negative 30 minus a negative 2 times 80 in the j. And then last thing I have is the k. 4 times 40 minus 5 times 80 in the k direction. And if I simplify all of this, I get the resultant moment. And I would get 30 in the I direction, minus 40 in the j direction, plus 60 in the k direction. And this is all in pound feet. And that's my answer for that. Okay. So now we're going to continue here, and we're going to talk about the principle of moments. So this is pretty much a continuation of what we've been doing so far, but this is the summation of moments at point O would be the Fx component of any one force, okay, times the distance from the point we're summing moments about here to that force, right? That's still that perpendicular distance to the one force. And then also I'd have another component of that force. So basically, let me actually pull back for a second and show you what's happening here without the other forces. So typically what we've been doing so far, we haven't been dealing with forces like this that you can't measure a perpendicular distance from. So you see here, it's a little bit difficult to get what this perpendicular distance d is. So if we're not able to get that, or we don't have that information, a really easy way of figuring out the moment about point O from these two forces, from this one force, is to split the force up into components here. So I take F, and let's say this is theta. I would have F cosine theta, and I would have F sine theta, right? And F cosine theta would be the distance from point O to the line of action of that force. So I would have this distance here, which is some y. And then the distance to F sine theta would be the line of action of that force, 2.0, which is some distance x. And then my total moment would be Fx times y, basically this F cosine theta times y, and it'd be positive because, again, remember, this would be counterclockwise, and then this force here would be negative about 0.0 going in the other direction, and we said that's F sine theta. Okay, so this is how, actually, wait, let me see, I think I drew these wrong. This one, my Fx would be clockwise. This should be negative. This is if I'm doing counterclockwise, positive. And then this would be positive, actually. There we go. The Fy here would be the counterclockwise. There we go. So we actually have MO equals Fyx minus Fxy, and this is if counterclockwise is positive. Okay, this here would be if clockwise is positive. So either way you write it is totally fine. Just make sure you specify which direction you're assuming is positive. Okay, now let's go ahead and try example 5. I'm going to do this a couple of different ways so you guys can see how it doesn't really matter how you approach the problems. You can get the same correct answer with multiple different types of solutions, okay? So whichever solution comes to your mind, or whichever solution makes the most sense to you, is the one that you should probably go with. So let's start with a possibility for solution number 1, okay? And what I'm going to do here is I'm just going to find the moment arm using trigonometry here, and just go ahead and say MO is equal to force times distance. Okay, so from trigonometry we can see my moment arm here to this force, this is the perpendicular distance from the line of action of F to O, here D is just equal to 3 sine and then 75, right? That's the angle it makes there. So 3 sine 75, and I end up getting 2.898 meters. Okay, I can go ahead directly, say MO is equal to 5 times 2.898, and I end up getting MO is equal to 14.5 kilonewton meters, and this is acting in the counterclockwise direction. Why? Because if I were to pull this force, it's moving counterclockwise around point O. Okay. All right, so let's try another solution now. Okay, now I'm going to do the second solution here the way I was describing earlier. I'm going to split this force up into components. So I'm actually going to start by drawing the X and Y direction here. And I can have an Fx component and an Fy component of the force, right? So I have my Fx component, which is just going to be 5 cos 45 and 5 sine 45, right? And the moment arm from point O to Fy sine 45, or at 5 sine 45 is going to be this distance. I'm going to call it dx. And then this vertical distance here to point O is going to be dy here. So now what we can do is we can split this up. We can say the sum of the moments about point O, counterclockwise is positive, is equal to, now Fx is going to produce counterclockwise rotation, right? I'm sorry, clockwise rotation, so it's going to be negative. So I'm going to have negative Fx times the moment arm dy, and then pick a different color I haven't used here. Let's see, orange. Okay, and then Fy is also going to produce that clockwise rotation. So it's also going to be minus Fy dx. So I'm just going to plug in here, and I get negative 5 cosine 45 times a moment arm of 3 sine 30 minus 5 sine 45 times the moment arm of 3 cos 30, and I end up with negative 14.5 kilonewton meters, and I know it's going in the clockwise direction, and I assume counterclockwise is positive, which is why my final answer is negative, which means it's really 14.5 kilonewton meters in the clockwise direction. That's what the negative means. It means it's opposite of what I had initially assumed. Okay, so you can see we got the same exact answer. And I'm going to show you one more way to do this, okay, where you can still get the same answer. Okay. Number 3. Okay, so I'm actually going to redraw this problem right here. Redraw this rod. And basically we have, let me see here, 5 kilonewton force. Should really be a little more like 45, so I'm going to fix this. And we have a 45-degree angle here. Okay, and we know that in this direction, oops, there we go, whoops. We have here 5 cosine let me see. So what we can do here, actually, I'm going to erase these axes. What I want to show you guys here is instead of putting, so remember that this rod makes a 75-degree angle with this horizontal, I'm sorry, this vertical system here. So what we can do is instead of putting the force into the Fx and Fy, I'm actually going to draw the axis along the rod like this and then perpendicular to that here. Let me try to draw this correctly so it's a little bit less confusing. So I'm drawing these axes along the axes of the rod, and now I can draw that 5 kilonewton force a little bit better. Okay. Now what I can do is instead of putting the force into components along the x and y, I'm going to use the axis of the rod. So I'm going to say that this here is actually 5 sine 75 and 5 cosine 75 because this angle here is 75 degrees that we make with the force to the tilt of the rod. And what happens here is basically I've made parallel and perpendicular axes, so you can call this almost like the x prime and the y prime axes, which are parallel and perpendicular axes. And what that does is it takes away the need to consider this force because it acts in line with point O. So you see there's no longer a moment arm. So the only force we have to consider now to get sum of moments about point O, counterclockwise is positive, is just Fy times dx. And Fy here, which is that 5 sine 75, acts in this direction, which is clockwise, so it's going to be negative. So if I plug in everything here, I get negative 5 sine 75 times 3. And I end up getting the same answer. MO is 14.5 kilonewton meter in this direction. So no matter which one of these options you picked, it's all the correct solution, all the right answer, all the same ID. Okay, so you're welcome to choose any of these types of solutions that come to your mind when you're trying to solve these problems. Okay, let's go ahead and try another example here. So we have a force F that acts at the end of the angle bracket here, and we want to determine the moment of the force about point O. Okay, so I'm not going to do three solutions. I'm going to do 2 solutions this time. I want to show you guys how to do this using a scalar analysis and then how to do this using a vector analysis. So solution number 1 is scalar. Okay, so what I want to do here, excuse me, I'm actually going to put this force into components along the x and the y direction. So I would have F sine 30 and F cos 30. And to some moments about point O, I'm going to assume counterclockwise is positive. I would have the 400 sine 30, and then let's figure out the moment arm now. So the 400 sine 30, the distance from the line of action of that force to point O is 0.2 meters. And let's confirm if that's going to be a positive or a negative. So the F sine 30 would be rotating in this direction, which is counterclockwise, which is positive, so I'm going to keep the positive there. Now the next step is the F cosine 30. So I have 400 cos 30. Moment arm there is going to be the distance from the line of action of F to point O, which is this 0.4. And I'm going to be wrapping around in this direction, which is clockwise, so I have a negative there. So here, my final answer is negative 98.6 Newton meters, and I can rewrite this since it's negative and I assume counterclockwise is positive. That really just means 98.6 Newton meters clockwise. And that's my answer using scalar analysis. So I'm going to show you how to also do this using vector analysis now. Okay, and what I want to do here is I'm actually, let me redraw, or actually I'll draw right on here. So for vector analysis, remember what I need to do is I eventually want to get all the terms required to say that MO is equal to R cross F. So I first need to figure out my R. R is going to be the distance from the point I want moments about to the force, the tip of the force, right? So this here is going to be my R vector. I only have one force, so I only need one R vector, okay? Now, to get from O to that point, the R vector, I need to travel 0.4 in the I direction, minus 0.2 in the J direction. And then I also need to break up my force into vectors, so I would have that 400 sine 30 in the I, minus 400 cosine 30 in the J. And once I do that, I can directly plug in to R cross F using my determinant. So I, J, and K. I'd have 0.4, negative 0.2. Really, I don't have anything in the K because this is 2D. So I can actually just completely get rid of the K column. I just put it in here for completeness sake. And I end up getting 0 in the I, minus 0 in the J, plus, so I really don't need to do anything with these zeros here, but I am going to need this for the direction of my moment, because remember, anything I cross J is going to give me a K. So I can disregard these zeros, but I need to remember I need the K direction in there. So then I have 0.4 times negative 346.4 minus negative 0.2 times 200 in the K, and I end up getting in the K direction, of course, terrible looking 8, okay, negative 86.6, negative 98.6 in the K direction, and that is in Newton meters. And I can leave that negative, it just means that it's going in the negative K direction. Okay, so for 2D methods, solution 1 is generally easier. You can see I just took one line of work as opposed to having to sit there and write out the cross product and do all of that pre-work to get the vector analysis. So typically what we do is for 2D systems, we stick to scalar analyses, and for 3D systems, we use vector analyses. Okay. Okay. Let's go ahead and continue here. So next thing we're going to do, we're going to talk about moment of a force about a specified axis. So sometimes we're interested in the moment of a force that produces some component or rotation along a specific axis. It might not even be the pure X or Y axis. It could be any important axis. And we kind of got a preview of that. This is why I showed you these 3 different types of solutions here. We actually were able to put these forces along 2 different axes, which were in line with the member in solution number 3 here. And so we're kind of talking about something similar here. We're going to use what we learned up to this point to solve this type of problem. And again, we can use either scalar or vector analyses for these problems. Okay, so the moment, this is in terms of scalar analysis, the moment of a force is going to be just MA is equal to F times dA. And dA, of course, is still the perpendicular distance from the line of action of the force to whichever axis it is that you want the moment about. Okay. When we're talking about vector analysis, we're going to have to define UA, which is the unit vector that's in the direction of the A-axis. And remember, the A-axis here is any axis that you want the moment about. So I'm going to write that here. Any arbitrary axis you want moment about. Okay, MA, so you'll need the position, the unit vector in the A direction. Okay, the moment of F about point O on the axis again is that MO is equal to R cross F. So the projection of this moment onto any other axis, let's just say A, an arbitrary axis, is MO, or the unit vector A dot MO. So really what I'm trying to say is here, we're going to take MO and we're going to multiply it by the unit vector in the A direction here. And that's how we can get MA. Okay, and in vector form here, it's just MA times UA. So the magnitude of A times the unit vector in the A direction. Okay, and that's kind of all spelled out here. We can use those same equations that we've been using to figure this out. Okay, so let's try this in an example here. So we want to determine the resultant moment of the three forces about the X, Y, and Z axes. Okay, so all we have to do, we're not being asked to sum anything up right now. We're just being asked to keep everything in their respective direction. So let's start with the X-axis and let's see what we're working with. So along the X-axis here, we have a 60-pound force. That is this guy right here. And there's a moment arm of 2 feet away. It's right there. And we're going to be adding 50 times another 2 feet away that this acts. Right, because the 50 acts at the corner here, and this corner is 2 feet away. It's kind of hard to see. I might be making it more complicated with that drawing. But the corner acts 2 feet away from the X-axis. And then plus 0 from that 40-pound force, because that acts through the same point. We don't act any distance away with the last force there. Okay. So that's going to be equal to 220 pound-feet in the X direction. Okay. Now, let's sum moments in the Y direction. Not 0. Used to writing that from equilibrium. We'll get to that later. Okay. That's equal to, I have the 50 again, which is going to be acting at 3 feet away. I'm going to uncircle what I had previously here. The 50 acts at 3 feet away right there. So I have 50. And that's going to produce a negative moment about the Y axis, so times 3 feet. And then this 40-pound force acts 2 feet away from the Y. So I'm going to have minus 40, still producing negative moment, times 2 feet away. And I get negative 230 pound-feet. And then I can sum moments about the Z direction. Counterclockwise is positive. And here you can see I don't have any contribution from the 50 around the Z-axis, right? There's no moment arm distance from F2 to the Z-axis. And I also have no contribution from the 60 because that also goes in line with the force. It's not acting in the Z direction there, right? So all I have is this 40, which is acting 2 feet away here. So I would have a negative 40 times 2, which would give me negative 80 pound-feet. Okay, what does the negative mean? It just means that it's acting in the opposite direction that was specified here. Okay, so any force that's parallel to an axis or that has a line of action that passes through the axis does not produce any moment or tendency for turning. So I want to make this very clear because sometimes it's a little bit confusing in 3D. So let's take this first equation right now. Okay, so the 60 and the 50-pound force contributed. The 40-pound force, why did it not contribute to the X direction? Because any force that's parallel to an axis does not contribute to rotation about that axis. Do you see how this is parallel? Therefore, the 40 is not included. So parallel force to an axis goes to no moment. Okay. Now, let's take a further look here. I'm going to cross this off. Okay. Now let's look at why we didn't include the 60. Well, same thing. The 60 is parallel to the y-axis here, right? Parallel. So we're not going to include the 60 there. Okay. Now let's take a look at the z-axis, or the z summation here. We didn't include the 50. Again, parallel force. Parallel to the, well, there we go, parallel to the axis, okay? We didn't include the 60. Why? Because the line of action crosses through that point. Crosses through that point. Okay? So there's no tendency or turning about that axis. Okay? So that's why we're not including those in the summation for any of these three. Okay. Now, the positive direction of moment of a force is determined, again, by the right-hand rule in these cases. So you're going to curl your fingers, or the fingers of your right hand, and your thumb in the direction of rotation, and your thumb is going to be pointing in the direction of that rotation. So you can see here 3 little right hands showing the direction of rotation along each axis. Okay. Okay, let's do one more example here. So example 8, we want to determine the moment MAB produced by the force F, which tends to rotate the rod about the AB axis. Okay, so what we're going to do, we're going to use vector analysis for this one. And I kind of already have shown you that vector analysis is pretty much the easier route to take typically when you're dealing with 3D problems. So just as a kind of like future direction for this class, when we deal with 3D problems, 3D problems, most of the time we'll be using vector analysis. And when we deal with 2D problems, we'll be using scalar analysis. So this is kind of a go-to. Okay, I've been trying to show you guys multiple different approaches and methods to use for this, but for the remainder, we're pretty much going to try to stick to vector analysis for 3D and scalar analysis for 2D. Okay, so this is a 3D problem here. So we're going to use the concept MAB is equal to the unit vector in the B direction dot R vector cross F vector, right? So this is how we can get the moment about another axis of rotation using the cross product of the force and the position vector and the unit vector at that point. Okay, so remember UB from our previous definition, the unit vector to be, this defines the direction of the AB axis. So this has to define the direction of the AB axis. That's the definition of this mathematical product here. Okay, so what does UB have to equal? The unit vector at B needs to be equal to the position vector divided by the magnitude of the position vector. So to get to point B, right, to get to point B, I need to travel 0.4 along the I direction, or the X, right? So I'm going from point A to point B. And I'm going to have to travel a plus 0.2 in the J direction, and then that's going to be divided by 0.4 squared plus 0.2 squared, and I end up getting 0.8944 in the I plus 0.4472 in the J. Okay, so remember the vector R is directed from any point on the AB axis to any point on the line of action of the force. That's that definition of transmissibility of a force. Okay, so example here, what do I mean by that? Basically, position vectors RC and RD. If I were to use RC and RD, I'm using this image here, okay, are suitable. Okay, I can use RBC and RBD as well. I can use any of those R's here that I want to. It doesn't matter. You can use any position vector from point A, right, directed to any point on the line of action of the force. Remember, this is the line of action of the force. I can use any of these pink position vectors that I want to use, and I can get the correct answer here. Okay, I can also go from point B to C and point B to D. That's what I have in the parentheses here. Okay, so use whichever one of those that you want to use and you'll get the right answer. Okay, for simplicity here, I'm going to choose RD. Okay, I'm going to choose RD because as you can see, all I have to really do to get to RD is go 0.6 on the I. Okay, and my F is equal to negative 300 on the K. So you can plug in any one of those, you'll get the same answer, but for simplicity, I'm just going to use RD. So I would have MAB equals the unit vector in the B direction dot R in the D, or sorry, RD cross F, and plugging all of this in, I get, I put the unit vector up here now. Oops, okay. 0.8944, this is how I can set this up, 0.4472, 0.6, this is the RD vector, and now I'm going to put in the F vector, and I end up getting this is the determinant here. (80.5 Newton meters), and this is positive. So what does that mean? It means that the moment acts in the same direction, MAB acts in the same direction as UB. As the unit vector. Okay. Now my Cartesian vector MAB, if I wanted to keep this in Cartesian vector, I would take my MAB, the scalar quantity I just solved for, and I can multiply it by my unit vector. So I can say that 80.5 times 0.8944 in the I plus 0.4472 in the J is equal to 72 in the I plus 36 in the J, and that's in Newton meters. Okay, so I can keep this in a Cartesian vector system as well. Okay. All right, so we're going to stop there, and we're going to talk about couples in the next video.